This is the Math12550 Exam 1 review, and I'm Dr. Tatyana Khodorovskiy, and in this video I'm going to do examples from the Exam 1 review of polynomial functions. Now this is by far the most difficult topic for Exam 1. So the first problem that I'm going to do is number 64, and there's lots of things we can do with polynomials. We can be given polynomial equations to solve, or we can be given factored polynomial functions, such as in this example, and asked to find all the zeros. We're asked to find all the zeros with multiplicities, and multiplicities are very important aspects of zeros of polynomial functions. Of the following functions, so the zeros or the roots is where the function is 0. So in this case, the function has been factored for us. And if the function is factored for us, a lot of the work is already done. And by all means, do not start multiplying things out. You're going to lose information. When a function is factored like this, you can get all the roots from it right away. So the roots, again, or the zeros, is where the function equals to 0. Now where can this equal 0? Function can equal 0 if one of its factors is equal to 0. So let's look at each factor separately. So this factor, x plus 3 squared, can only be 0 if x equals -3. So the factor x plus 3 squared gives us the root x equals -3. And this root has multiplicity 2 because the factor of x plus 3 appears twice in this factorization. The m is signifying the multiplicity of the root. The next factor is 2x minus 1. Now, for 2x minus 1, what root does this factor contribute? Well, whenever 2x minus 1 equals 0. So 2x minus 1 equals 0 is when 2x equals 1, or is when x equals 1/2. Now this root appears with multiplicity 1 because there's no exponent on this factor. The third piece, x plus 1 cubed, gives us this root. It gives us the root x equals -1, and it appears with multiplicity 3. So to summarize, the zeros are as follows: at x equals -3 with multiplicity 2, at x equals 1/2 with multiplicity 1, and x equals -1 with multiplicity 3. And so this is the final answer. You can record it like this. Now observe something else. If you add up all the multiplicities, here, you have 2 plus 1 plus 3 equals 6, and the degree of the polynomial is also 6. This will always be the case. If you add up all the roots with their multiplicities, you're always going to have something equal to the degree of the polynomial. If I multiply this polynomial all out, I don't have to do that. It's going to take a very long time. It's definitely going to be, the first term is going to be 2x to the 6 and ... something very, very long and complicated. But the degree of that polynomial is going to be 6. This means it's going to have 6 roots counting multiplicities. So the final answer here is that this degree 6 polynomial has 3 distinct roots. X equals -3 appearing with multiplicity 2, x equals 1/2 appearing with multiplicity 1, and x equals -1 appearing with multiplicity 3. in the next problem, we're not given the luxury of a factored polynomial. In fact, we're just given a cubic or a degree 3 polynomial that looks like this, and we need to find all the values of x for which this polynomial is 0. Now this is a degree 3 polynomial, so we need 3 roots counting multiplicities. This could either be 1 root with multiplicity 3, it could be 3 roots with multiplicity 1, or it could be 1 root with multiplicity 1 and 1 root with multiplicity 2. And very few cubics in an algebra course, you may have factored a cubic with grouping. Very, very few cubics are going to be, you're going to be able to factor with grouping. So the number 1 course of action in this class when you're faced with an equation like this is to first look at the possible rational roots. So the possible rational roots of the polynomial are all numbers that look like p over q, with p a factor of the constant term and q a factor of the leading term. So all such combinations are plus minus 1, plus minus 2, plus minus 4. These are all the factors of negative 4. And on the bottom, plus minus 1 and plus minus 3. So the possible rational roots are, if you look at all combinations of numerators and denominators, is going to be plus minus 1, plus minus 1/3, plus minus 2, plus minus 2/3, plus minus 4, and plus minus 4/3. So this does not say that any of these numbers are roots. The rational root theorem only says that if there is a rational root solution to this polynomial, then it must be one of these 12 numbers. And so the best course of action is try to figure out which is indeed a root. So if this polynomial evaluates to 0 at any of these 12 numbers, then we have found ourselves a root. So we're going to try. We're going to try, and there's no rhyme or reason to which one you want to try first. Usually you want to try the integer one first, just because they're easy to plug in. So first we're going to try x equals 1. Plug it in. 3 times 1 cubed plus 11 1 squared plus 8 times 1 minus 4. And you don't really need to compute this in detail, you just need to decide is this 0 or not 0. So this is going to be 3 plus 8, it's going to be 3 plus 11 plus 11 plus 8 minus 4. Whatever it is, it's definitely not 0. 1 is not a root. Okay, we continue. Let's try x equals negative 1. Well, this is 3 times negative 1 cubed plus 11 times negative 1 plus 8 times negative 1 minus 4. Well, this is going to give us negative 3 plus 11 minus 8 minus 4. This is still definitely not 0. I'm going to keep going. Let's try x equals 2. Is that going to work? Well, 3 times 2 cubed plus 3 times 2 squared. So 3 times 2 cubed plus 11 times 2 squared plus 8 times 2 minus 4. This seems to really not be 0 because this is a fairly big number. This is 24 plus 44 plus 16 minus 4, that's definitely not 0. Let's try x equals negative 2. This is 3 times negative 2 cubed plus 11 negative 2 squared plus 8 times negative 2 minus 4. And we're going to get negative 24 plus 44 minus 16 minus 4. Aha, we got one. It does equal 0. What this means is that since f of negative 2 equals 0, it means that x equals negative 2 is a root of f of x. So we got one. We can continue going and try the other rational roots, and maybe we'll even get some success. But once we have, if you want all the solutions to a cubic and we have one root, the most economical course of action is to do long division and divide and find out what's the quadratic factor when you factor the root out. So this means, so what does this mean? If f of negative 2 equals 0, x equals negative 2 is a root of f of x. So this means that f of x has a factor of x plus 2. Well, if we know it has a factor of x plus 2, we can do long division. So x plus 2 is going to go in to our cubic polynomial. We have 3x cubed plus 11x squared plus 8x minus 4. We're going to do long division. X goes into 3x cubed, 3x squared times. 2 times 3x squared is 6x squared. We're going to subtract, so we get 5x squared. Bring the next term down. X fits into 5x squared 5x times. Now we're going to subtract 5x squared plus 10x. Subtracted, we're going to get negative 2x, and we're going to bring down the minus 4. And indeed, it fits in there nicely. And so we have broken up our cubic into a linear term and a quadratic term. So what do we know? We know that now our function can be factored into x plus 2 times 3x squared plus 5x minus 2. And now this is a quadratic. Quadratics we can either factor by factoring or the quadratic formula. Again, you may be able to factor this by factoring, but if you don't see it, you should use the quadratic formula. So this is going to give us the root x equals negative 2, and let's see what roots this gives us. This is going to be x equals 2 minus 5 plus or minus square root of 25 minus 4 times 2 times 3. This is a negative 2. Again, getting signs right is very important. Divided by 2a, so that divide by 6. So x equals to minus 5 plus or minus square root of 49 divided by 6, which is minus 5 plus or minus 7 over 6. So these are indeed rational roots. And so finally, all the solutions are x equals negative 2, x equals negative 12 over 6, which is another negative 2, and x equals Negative 5 plus 7, that's 2 over 6, that is 1/3. So these are the roots, so we have the root x minus 2 actually appearing in multiplicity twice. So all the solutions here are as follows. X equals negative 2 with multiplicity 2. X equals 1/3 with multiplicity 1. This is the final solution to this problem. So this equation has two solutions, x equals negative 2 and x equals 1/3. And if we want to fully factor this cubic, we're going to have x plus 2 squared times 3x minus 1. So in general, when you're faced with a hard problem like this, when you need to find all solutions of a cubic, your first course of action is to find all the possible rational roots by using the rational root theorem. You look at all the possible rational numbers that can occur if the factors of the constant term are in the numerator and the factors of the leading coefficient are in the denominator. In this case, we got a list of 12 numbers, and then we start trying them. This is a bit of a trial and error. If you try all the possible rational roots and none of them give you 0, then you're kind of stuck and you can't proceed further. Usually that's not going to be the case. One of them is going to work. In this case, we tried x equals 1. We plugged it into our polynomial and it did not give us 0. This meant that x equals 1 is not a root. Same thing happened with x equals negative 1 and x equals 2. They were not roots. However, when we plugged in x equals 2, we got that it equals 0. This means that f of negative 2 equals 0, which means x equals negative 2 is a root of f of x, which means that f of x has a factor of x plus 2. Well, if our cubic has a factor of x plus 2, that means we can do long division without a remainder. And when we did long division, when we divided our cubic by x plus 2, we got the quadratic function, 3x squared plus 5x minus 2. Once we have split up our cubic into a linear term and a quadratic term, then the only thing left to do is solve the quadratic equation by using the quadratic formula or factoring or completing the square, whatever method you prefer. And we got that the roots of this quadratic equation were negative 2 and 1/3. And in fact, if we would have continued plugging in all the possible rational roots, when we plugged in 1/3, we would have gotten that the answer was indeed 0. That's another way. However, that is computationally more difficult. And anyways, in the end, we got that there's two possible values of x that will solve this equation, x equals negative 2 and x equals 1/3. The next problem that we're going to do is number 77. This problem asks us to do things in the reverse direction. Number 77 asks us to construct a polynomial with the following. The following roots. So before we were given a polynomial, factored or unfactored, and we needed to find the roots. Now this is vice versa. We are told that there is a root of x equals 3 and x equals 5 of multiplicity 1. We're also told there is a root of x equals negative 1 with multiplicity 2. We're told there are roots of square root of 2 and negative square root of 2, each having multiplicity 1. Roots like this will always appear in pairs. And we're also told that there is a root of minus 2i, an imaginary root, of multiplicity 3. Now, this is the information that we were given. whenever we have an imaginary root to a polynomial, it must always come in pairs. Remember this fact. If a plus bi is a root, then so is a minus bi. Its complex conjugate is also a root. So, although we weren't told this, it has to be that x equals 2i is also a root of our polynomial, because all complex roots come in pairs with their conjugates, and it must also have multiplicity 3. So now let's look at the corresponding factor of every single root. So the root x equals 3 is going to give us the factor x minus 3. The root x equals 5 is going to give us the factor x minus 5. The roots x equals -1 with multiplicity 2 is going to give us a factor of x plus 1 squared. Now this will come in pairs. The two radicals are going to give us these two factors. They're going to give us the factor of x minus radical 2 and x plus radical 2. But we can simplify this into x squared minus 2. So it's going to give us this factor of x squared minus 2. Now the complex roots, they're also going to come in pairs. The complex roots are going to give us this factor, x squared plus 4 to the power of 3. Because recall, if we have x squared plus 4 equals 0, if that is a factor of our polynomial, then x squared equals -4, x equals plus or minus square root of -4, which is plus or minus 2i. And we have 3 copies of these. And so we're going to have factor of x squared plus 4 cubed. Again, notice the degree of this polynomial. We're going to add up all of these. We're going to add up 1 plus 1 plus 2 plus 1 plus 1 plus 3 plus 3. And we're going to get 12. So the degree of this polynomial is 12. When we add up all the roots with its multiplicities. And finally, if we want to write down an expression for our polynomial, we don't know what the leading term is. We can leave it as a constant. We weren't told enough information to figure it out. If we were told the y-intercept, then we could have figured it out, but we weren't. So we can just leave it as an unknown constant a. And then f is just going to be a product of all the factors that we have found. Notice the degree is 12. We have 1 plus 1 plus 2 plus 2 and then plus 6. And so the final answer for this problem, we have wrote an expression for a polynomial which satisfies all of these properties. This polynomial has a root at 3, given by the factor x minus 3. It has a root at 5, given by the factor x minus 5. It has a root of x equals -1, corresponding to the fact of multiplicity 2, corresponding to the factor x plus 1 squared. It has a pair of roots, radical 2 and negative radical 2, corresponding to the factor x squared minus 2. And it has a complex root of -2i, Therefore, it also has another complex root, the conjugate of 2i, each appearing in multiplicity 3, giving us the factor x squared plus 4 cubed. That was number 77. In a final problem for this video, we're going to do number 80. We're going to sketch a graph. We're going to sketch a graph of the following polynomial. This is negative 1 over minus 1 over 1/25, and some constant, and we have x minus 1 squared, we have x plus 1 squared, and we have x minus 5 cubed. And so first we want to figure out, when we want to sketch the polynomial, we want to figure out its end behavior and its local behavior. So its end behavior is going to depend on two things. It's going to depend on its degree, and it's the sign of the leading coefficient. The degree of this polynomial is going to be 2 plus 2 plus 3 is going to be 7, so it's odd. The leading coefficient, is negative. So an odd polynomial, an odd degree polynomial with negative leading coefficient is going to have an end behavior that looks like this. So as x goes to negative infinity, the function goes to infinity, and as x goes to infinity, the function is going to go to negative infinity. That's the end behavior. Now the local behavior is going to be given to us by the roots. Well, we have a factor of x plus 1 squared. This is going to give us a root of x equals 1 of multiplicity 2. X equals negative 1 of multiplicity 2. So this is x minus 1 squared is going to give us the root x equals 1 of multiplicity 2. We also have x plus 1 squared. That's going to give us the root of x equals negative 1 of multiplicity 2. And finally, we have another factor, x minus 5 cubed. And this piece is going to give us the root x equals 5 of multiplicity 3. Again, notice all the multiplicities are going to add up to 7, the same as the degree of the polynomial. So now we are ready to sketch the polynomial. Whenever you're sketching the polynomial, it's important to show where the roots are, where is the polynomial hitting the appropriate roots. And in this case, since we are given that leading coefficient, we could also figure out where the function intersects with the y-axis. So if we were to plug in f of 0, we would have gotten that this is negative negative 1 over 1/25 times negative 1 squared times 1 squared times negative 5th squared, and that this in fact just equals to 1. So the y-intercept is 0, 1. And so we would plot all these points on the graph. So we know the graph must go through the root negative 1, the root 1, and the root 5. We also know there's a y-intercept of 0, 1. And now we begin drawing by looking at the end behavior. In the end behavior, this is an odd degree that's going to come in from this side. So this polynomial is going to start coming in from the second quadrant here. And now the root at -1 has multiplicity 2. If a root has even multiplicity, the graph does not cross the x-axis there. It simply goes towards that root and then turns right back around, touching it just like the parabola x squared does. Now goes through the x-intercept and it does the same thing at the root x equals 1. It touches the graph at this point and then turns right back around. Now for roots with odd multiplicity, the graph of the function is going to cross the x-axis, but because the root is 3, it's going to still flatten out a little bit before it crosses. If the multiplicity was 1, it would just cross like a linear function. So here is a very good sketch of this polynomial. It has roots of multiplicity 2 at -1 and 1, and we see this because the graph just touches the x-axis and then turns right around. And then it has a root of multiplicity 3, an odd root higher than 3, and those roots look like they're crossing the x-axis, but they have to flatten out a bit next to that root. And so when you're studying polynomial functions, it's important that you go back and forth between the algebraic expression, the graphical expression, and the information about the roots of a polynomial, and know how all these three things are intertwined.